So in general, there's only two types of equilibrium problems. One where they're asking you to solve for the Ka and they're giving you concentrations, or they're giving you the Ka and they're asking you to solve for concentrations. In this case, they're giving you Ka, but they're giving you pH. So if they're giving you pH, that must be a way for us to figure out concentration, or else we couldn't solve this. So I'm going to start off here and write my equilibrium expression for H3BO3, just so we have that in our back pocket. And remember, whenever we're writing an equilibrium expression, we take whatever they give us and we throw it into water. Now this is aqueous. We're going to throw that into water, H2O. And remember, this is equilibrium, so we're going to write the fancy equilibrium things. And since this is an acid, what is it going to do? It's going to give up a hydrogen to this base. Remember, water can be both an acid or a base. And when we do that, we're going to end up with, and I wrote PO3. This is in reality is BO3. Easy mistake because we don't use this all that often. When we write out the equation, it's going to be equal to H2BO3 minus plus H3O plus. Now, if we were to write a Ka expression for this, wouldn't we write it as concentration of H2BO3 minus? And if you're wondering why was it a minus, we ripped off a hydrogen from this, right? This is neutral as is, right? So if I rip off a hydrogen from something that's neutral, it's going to become negatively charged, which is why we put a negative right here. Then on the bottom, we're going to have, oh, I didn't finish the top. We still have H3O plus up here, and we're going to write H3O plus like this. And then on the bottom, we're going to write H3BO3. Now, we need to know what we have to put in these spaces right here. So what are we going to do? We're going to start off with what they give us in this problem, and they give us a 1.4 molar solution of boric acid. So we're going to set up an ice table right here. We're going to go I, C, and E. And we're going to start off with 1.4 molar of this. Now, do we care about the liquid here? Not even a little bit. So this is a nothing line right for us. And then over here, we start off with nothing, right? So we're going to have nothing here and nothing here. Now, since this is if you look at our coefficients, this is a 1 to 1 to 1 ratio. If we were to lose anything, let's say call it, I don't know, X, if we were to lose X from this, wouldn't we gain X here and gain X here? True story, right? So then our equilibrium value wouldn't be 1.4 molar minus X. And I'm going to get rid of the molar right here because we don't want it in messing with our calculations. And we have X here and X here. So all these values we're going to plug back into our equilibrium expression. And just to make it a little bit easier for us to see, and through the magic of me having an iPad, I'm just going to take this guy right here and I'm going to bring it down here. And we're going to plug in our variables into there. So what are we going to have here? Our Ka is going to be equal to X times X all over 1.4 minus X. And that's going to be equal to our Ka. Now, here's the problem. If we know what our X is, can't we plug all these variables in? And by the way, you might be inclined to make this go to 5% rule. We don't know what the Ka value is, so we can't know if this can be gotten rid of or not. But if we were able to know what X was, can we plug X in all of these three places? And when we do that, we'd be able to solve for our Ka. Well, how do we do that? Well, they tell us that the pH is of the solution is 4.55. Now, what do we do with that? Well, we know this. If we want to figure out our H plus concentration, that is equal, that's supposed to be a square bracket, is equal to 10 to the negative pH. So if we want to figure out our H plus concentration and we put it to 10 to the negative 4.55, and here's where I wish I'd been a little bit more judicious with my spacing. This expression right here, that's going to allow me to figure out my H plus concentration. And when I put my H plus concentration down on my paper, my H plus concentration is going to be equal to 2.818 times 10 to the negative 5. Isn't that also equal to X? So since we know at equilibrium that this is my H3O plus concentration, Once we were able to solve for H plus from our pH, we can then plug in this value in all three of these spaces right here. So I'm going to go ahead and do that for you because I can, but wouldn't that be 2.818 times 10 to the negative 5 times 2.818 times 10 to the negative 5 on the top, all over 1.4 subtract 2.818 times 10 to the negative 5, and that's going to be equal to my Ka. Now, really quickly here, this 1.4, when they gave us the problem, they gave us it with two significant figures right here, and the 1.4, they gave us just, again, two significant figures. When we plug the numbers in, we're going to end up with a Ka value of 5.672 times 10 to the negative 10. Now, by the way, if you're like wondering about this expression right here, do you know what happens when you take this and you subtract it from this? This is essentially 0.000281.8. And if I were to add that to 1.4, do you see how this right here is completely negligible? So in reality, this wouldn't really matter to us. But this right here, this is our Ka value. Remember, we only can use the significant figures they give us in the problem, and they want the correct sig figs. We use 2 up here, so my answer down here needs to have 2. So this would be 5.7 times 10 to the negative 10 equals my Ka. Apologize for my messiness on this, but hopefully it has made sense.